In today's lecture, we'll be discussing a paper titled Prescriptive Analytics for Flexible Capacity Management. This paper was published in Management Science in the year 2022. So, what is prescriptive analysis? So, in prescriptive analysis, we have a predefined goal, and we use data to prescribe a course of action to achieve this predefined goal. So next term in the title is flexible capacity management. So I'll introduce this with the help of an example. Suppose we have a car rental company, Ola, and they have a fleet of cars, and they provide two sorts of cars. So first is Ola Mini and Ola Prime, and each car has some capacity available. So IM for Mini and IP for Prime, and over the course of the day there will be a demand DM for Mini and DP for Prime. Suppose that demand for Mini exceeds the total available capacity and Prime has some capacity idle. So what Ola does is they allocate the remaining Prime, the idle Prime cars, to customers who had booked Ola Mini, and this does not cost the customer any extra charge. So the customer enjoys the prime car by paying the price of Mini. So what essentially Ola has done is, so they are able to meet the demand for the pro of this reallocation is that they are able to meet the demand for the customers, but the con is that they are using a costly resource to meeting this demand. So this capacity and demand matching, so this problem is further incremented by the fact that the capacity decisions have to be taken over the course for over a long duration, so that can be for a week or a month, but the demand, it changes hourly and it changes daily. So the aim of this paper is to determine right capacities for various resources. So that is the basic premise of this paper. So essentially we have a two-stage problem. So the firm makes a capacity decision before the planning period. It then observes the demand, the actual demand, and then it reallocates the capacity. So traditionally this problem is solved in two steps. So the first step is to estimate this demand distribution from data, and then the problem of the stochastic problem is then optimized. But the issue here is that errors in the first step get magnified after optimization. So if the first step has a lot of errors, the optimization does not help that much. So what this paper proposes is, so if we have a historical data and we have features of the demand, so we can directly use it, the algorithms that they have given, they directly prescribe the capacity vector. So what should be the number of mini cars or what should be the number of prime cars. Next we come to the problem formulation part. Suppose the firm is providing I service lines and the planning periods are represented by small t that go from 1, 2 and up to capital T, and we have a demand variable dit, so it means service I demanded in period T. So this is the demand distribution that we do not know, but what the firm has in its hand is the demand data. So the data, we have n data points, so each data point has a demand for each service line and the corresponding features. So the service lines are following a hierarchy. So j equal to 1 is the most flexible. So for example, the prime cars are the most flexible because they can fulfill the demands for the mini cars, and the firm makes a decision q vector, so that is the decision variable. So this is how many cars of each service how many resources of each service line should be kept at hand, and the important thing to note here is that this decision is to be made prior to the first planning period. After the customers start arriving, that is the demand starts coming, so we have the observable demand, small d vector. So that is again what is the demand at each time for each service line. So observing this demand, we reallocate the cars. So the reallocation variable is y, and there is a penalty ci attached for each demand that is not fulfilled. And after reallocating some cars, we get some additional profit, so that is represented by aij. Now I'll go to the paper to and we'll look at the problem statement. So here we see the problem in two stages. So in the first stage, I make a decision. So the decision is q vector. So the q vector must be selected so that the expected profit for all the time periods minus the cost of having the resources is maximized. So after then we go to the stage 2 after we observe the demand d vector. So in stage 2 we maximize the value, we choose the value of reallocation so that the profit obtained after the reallocation is maximized. So this is the positive profit obtained after reallocation, and this is the cost associated with the missed demand. So both these equation will be subjected to some constraints. So first is the demand constraint, and the second is the resource constraint. So in demand constraint, whatever we are reallocating should be less than or equal to the demand. And again in the resource constraint, the reallocations should be within the resources we have. So instead of following a traditional approach where we first estimated the demand vector D and then solving the problem, so in this scenario, so in the new scenario of prescriptive analytics, so we directly prescribe the optimal decision vector Q that will minimize the loss when a new feature vector x vector is provided. So the loss function is given in equation 2. So the first term is the first term is the x post optimal profit, and the second term is the profit associated with the capacity decision q vector. So when the demand realized is d. So the authors have given two approaches for solving this problem. So the first approach is the weighted sample average approximation approach, or the WSAA approach. So I will skip the maths part for this. And the second approach they have given is the kernelized empirical risk minimization approach. So I will skip the maths again. You can go through the paper if you are interested. Next, we have a case study in which the authors have used these two approaches to see if their approaches provide any useful results or not, any useful improvement over the traditional methods or not. So in the case study, we have a company who wants to sort its mail. So the mails that are coming in are of different types. So letters, parcels, newspapers, advertising material, and so on. And they have different service lines. So labor for different skill set is used in different service lines. So they have manual labor, they have labor that uses the semi-automatic sorting machines, and they have the labor that is using the fully automatic sorting machines. So the thing to note here is that the person who is operating the fully automatic can do it, can also operate the semi-automatic, and can also do it manually. And but the manual person cannot go higher in the hierarchy. So the person who is sorting manually cannot operate the semi-automatic machine. So they have a data available for 209 weeks, and 162 elements are present in the feature vector. 5 different evaluation methods are provided to obtain the capacity vector Q. So the first two are those that are proposed by the author. So that is the KERM and WSAA. The third is the SAA, sample average approximation. So in this we do not consider the feature vector. So instead of having the weighted feature vector, we just replace it with equal weights of 1 by n. And the fourth is the SVR SEO, and the fifth is the ARIMA SEO. So after obtaining the values of the gap from the optimal profit is represented in the figures. So here we see that weighted SEO performs the best, and the KERM is the second best, and SAA is the third best. So from this figure we can also compare the role of the features. So SAA and WSAA only differ in the use of the features. So we see that the authors also take a term called as a coefficient of prescriptiveness P. So this measures the reduction of gap to the optimal profit relative to SAA, and we see that the features have substantial value in the final solutions because the WSA is more efficient in exploiting the prescriptive content than KERM, and that is more efficient than SAA. Further analysis have been done to check the impact of service level and upgrade profitability on the performance of the different approaches. So first we come to the impact of service levels. Impact of service levels on the absolute gap to optimal profits. So we see that at service levels of 50%, two featureless approaches, SAA and ARIMA SEO, lead to substantially lower performance than those approaches that account for features. However, as we move to a higher service level, SAA's performance improves significantly and matches with WSAA and KERM despite being featureless approach, because the focus at higher service level is on avoiding stockouts and thus keeping a higher capacity at hand. Another thing to note here is that for service level range from around 10 to 70%, the KERM approach outperforms WSAA, but for very high service level, WSAA outperforms KERM. So the reason can be found in this figure B. So here the coefficient of prescriptiveness goes down of KERM at very high service levels, which means that KERM stops exploiting the features available. So next comes the effect of upgrade profitability. So the curve is drawn for two service levels, 50% and 90%. So we see that all approaches benefit similarly from an increase in the upgrade profitability. So higher is the value of this alpha, so it becomes more important to use the capacity of service line 1 to meet the demand of service lines 2 and 3. Coming to the conclusions of the paper. So this paper proposed two data-driven distribution-free prescriptive analytics approaches for solving a complex two-stage capacity planning problem with multivariate demand and vector valued capacity decisions, and the results suggested a substantial performance improvement using their prescriptive analytics approach. Thank you.